Reduced strategic form. Not all extensive games have non-trivial subgames, and one may also be interested in equilibria that are not subgame perfect. In Figure 3.3, such an equilibrium is the pure strategy pair R-S-L. Here player 2 is indifferent between her moves L and R because the initial move R of player 1 means that player 2 never has to make move L or R, so player 2 receives the constant payoff 3 after move R. If a play actually reached player 2's information set, move L would not be optimal against S, which is why this is not a subgame perfect equilibrium. Player 2 can in fact randomize between L and R, and as long as L is played with a probability at least 2/3, RS remains a best response of player 1 as required in equilibrium. In this game, the pure strategies RS and RT of player 1 are over-specific as planes of action. The initial move R of player 1 makes the subsequent choice of S or T irrelevant, since player 1's second information set cannot be reached after move R. Consequently, the two payoff rows for RS and RT are identical for both players. In the reduced strategic form, moves add information sets that cannot be reached. Because of an earlier on move are identified in Figure 3.3, this reduction yields the pure strategy, more precisely equivalence class of pure strategies. R star where star denotes an arbitrary move. The two reduced as well as unreduced pure strategies of player 2 are her moves L and R. The reduced strategic form of Figure 3.3 corresponds to the bi-matrix game 3.18 of R star is taken as the first strategy top row of player 1. This game is degenerate even if the payoffs in the extensive game are generic because player 2, irrespective of her own move, receives constant payoff 3 when player 1 chooses R star. Once a two-player extensive game has been converted to its reduced strategic form, it can be considered as a bi-matrix game, where we refer to its rows and columns as the pure strategies of player 1 and 2, even if they leave moves at unreachable information sets unspecified. The concept of subgame perfect equilibrium requires fully specific strategies rather than reduced strategies. For example, it is not possible to say whether the Nash equilibrium R star L of the reduced strategic form of the game in Figure 3.3 is subgame perfect or not, because player 1's behavior at his second information set is unspecified. This could be said for a Nash equilibrium of the full strategic form with the two rows RS and RT. However, these identical two rows are indistinguishable computationally, so there's no point in applying an algorithm to the full rather than the reduced strategic form, because any splitting of probabilities between payoff identical strategies would be arbitrary. If one is interested in finding subgame perfect equilibrium, one should use algorithm 3.9 at each stage of that algorithm. The considered games have by definition no further subgames, and the equilibria of these games can be found using the reduced strategic form or the sequence form. A player may have parallel information sets that are not distinguished by on earlier moves. These arise when a player receives information about an earlier move by another player. Combinings of moves at parallel information sets cannot be reduced, which causes a multiplicative growth of the number of reduced strategies. In general, the reduced strategic form can therefore still be exponential in the size of the game tree.